All right, this video is going to cover analysis of second-order systems in the time domain. So we have a few different representations for second-order systems. The typical second-order system is our mass spring damper we've seen in the past. Other ones can be combinations of RLC elements. That's another way to have some second-order systems. So what's the difference between first order and second order? First order would have one state variable, so one eigenvalue. Second order would have two state variables, so two eigenvalues. And we have three representations to look at in this class. We have state space, which is two first order ODEs. So x1 dot is equal to x2 dot is equal to our typical negative k over m times x1 minus c over m times x2 plus 1 over m times u. We have, and as an alternative, one second order ODE. So if we combine all those terms together, we would have m d double dot plus c d dot plus kd is equal to u. And now we're going to have a new representation. So we're going to divide by that m and rename a lot of these terms in the middle here. So we're going to have d double dot plus 2 zeta omega n times d dot plus omega n squared times d is equal to 1 over m times u. So pretty much all we've done is divided by m and just replaced, c over m with this term right here, k over m with this term omega n squared right here. And that's how we're going to solve for these new variables, zeta and omega n squared. And those are the natural frequency and the damping ratio. So omega n is our natural frequency. That is the frequency of oscillation if there was no damping or resistors or anything like that that wastes energy in the system. So, for example, for this example specifically, omega n squared is equal to k over m. You could see that from the math from the last two equations. So omega n is plus or minus the square root of k over m, and we usually say the positive one for a positive frequency. Now, zeta is our damping ratio. That describes the amount of damping in the system. And so for this example, we can go through and solve that zeta is equal to c divided by 2 over square root of mk. So we have both of those terms now. So there are different types of second order systems. So we have undamped second order systems, which are marginally stable systems. For the second order systems we tend to look at, it means that the system oscillates forever. We have an output of like a sine wave, something like that. An underdamped system, we have the free response is oscillatory, but it dies out over time. So that's like a sine wave multiplied by an exponential decay. An overdamped system is when the system has so much damping that there are no oscillations in our free response at all. It just looks like two exponential decays combined together. And then critically damped is the border between underdamped and overdamped. You can think of it as like the fastest version of overdamped. Now, some additional parameters for specifically an underdamped system. So this is the response, a typical response that you would have for an underdamped system. If you put in some sort of input into it, maybe a constant input into the system. So we can see that looks like a sine wave, but it's decaying over time, reaching its steady state value. So we have three different variables here. MP is the maximum overshoot. That is the amount the first oscillation exceeds the steady state value by. So it's this distance right here. It's that value. TP is the peak time. So that's the time at which the maximum overshoot occurs. And then TS is our settling time. It's a time at which our oscillations stay within that plus or minus 2% of the steady state value, similar to 4 times tau for our first order linear systems. So it's essentially how long it takes for this system to settle down to 2% of its steady state value, within 2%. And that is going to cover analysis of second order systems in the time domain.